Okay, well, we'll get started then, and we'll try this out. All right, so we're continuing on in Chapter 4. On Wednesday, we said when describing a relationship between two numeric variables, there are three things we want to talk about. Okay? Can you guys mention this? Remember those three things? The trend or direction, the strength, and lastly, the shape. Okay? All right. So, sorry, let me... Okay, so we have a numeric summary that will tell us the trend or the direction and the strength. Okay, so this numeric summary is called the correlation coefficient. Okay, or just the correlation. Okay, sometimes we'll just the correlation coefficient. And the symbol is R. R can take on any value between -1 and 1 inclusive. Okay? When R is close to 0, the strength is weak. When R is close or far from 0, the relationship is strong. Okay. And if R is positive, then the direction is positive. And if R is negative, then the direction is negative. Simple enough. There's a small catch though, okay? R will not tell you the shape. Okay? R is not going to tell you the shape of the relationship, and so you can have, and you can always throw two numeric variables into R, into the formula to get correlation, and it's going to spit back a value. But our interpretation about strength and direction only makes sense if the relationship is linear. Okay, so our interpretations about R only work when the relationship is linear. Okay, and so the only way for us to tell if a relationship is linear or not is by creating a scatter plot. Okay, so we must first create a scatter plot. Okay, I'm going to ask a clicker question in a moment, so make sure you have your clickers ready. All right, let's see if this works. It seems to be working, this clicker thing. Oh, it's already running, it says. Oh, here we go. Oh, no, that's not it. Where is it? Okay, so we'll start a new session. All right, don't do that. Let's see. Okay. All right. So our first question. So here's a scatter plot, and start clicking away. I'll give you guys a minute to get your answer choices in. Okay, I'm going to call time there. All right, let's see what we got. Okay. And the answer is indeed B. Okay, so it's there is a slight positive trend here. Okay, you can tell because there's open gaps down here and up here. Slight positive, but there's quite a bit of scatter. So it's a weaker relationship. B is 0.5. You might be like, well, why isn't it 0.2? Okay, this is coming straight from our textbook. Okay. So I'm not making this up here. So that's this diagram right here. I just cut off the axes. It says R is 0.48, and we can look at a few other diagrams here. So we can see here we've got when you've got them all in a perfect straight line, no scatter. R is 1, so a strong relationship there. So here, so this is. You know, if we measure your height in inches and we measure your height in centimeters, you're going to have a strong correlation, because if we know your height in inches, we know exactly what your height will be in centimeters. Here, this is a very strong positive relationship. All of these, you know, we first have to plot them to make sure they're linear, and if they're linear, then we can apply our interpretation of correlation. This is strong positive. We've got you know, very little scatter. This is R, like 0.98. It says life expectancy for men, life expectancy for women. So this is probably from country to country. This is probably like, I think Japan has the highest life expectancy right now, both for men and women. And, you know, other developed nations, you've got high life expectancy for men and high life expectancy for women. You know, here's a slight oddity where you've got you know, lower life expectancy for women than men. And I don't know what country that is, but overall, you can make very good predictions. Okay, and we can see as the scatter increases, it goes down to 0.72 here. This is people's height and their weight. The correlation between that says about a 70%, 0.72. correlation, height measured in inches and weight measured in pounds. Okay, this has less scatter. R is 0.19, and here we've got R equal to 0. Actually, that was going to be my next question here. So, all right, everybody get your free point here then. For this one, the correlation is approximately, okay. So click. Somebody clicked D. Who's doing that? All right, so after you click, you can click the other one and it will change your answer. So correlation. Everybody should be clicking A. I don't know why I'm getting Okay, good. Well, somebody has clicked the wrong thing. Okay, now everybody's clicked correctly. All right, good. Okay, wait, what just happened here? How do I, Oh, there it is. Okay, very good. Everybody gets that one correct. because I did this wrong. Okay. All right, so that shows the relationship there. Oh, and then I'll just flip to the next page. So these are I'm just putting these up just because it's much easier than me trying to put a whole bunch of dots in your notes. But I mean, you can recreate these. These are just straight from your textbook. And then so here we've got the negative side. Okay, so literacy rate and total births per women, negative correlation. Total number of football carries and yards gained per carry, also negative correlation, but weaker. And as we go further and further, they get more and more negative until we get r equal to -1, forming a perfect straight line. Okay. So r will tell us the strength and the direction of a relationship. Okay. All right. Okay. A few notes about R. Okay. The correlation. R is very correlation is very susceptible to outliers. So be careful. Okay, so for example, let's say we have shoe size and IQ. Okay, we should see no correlation, right? We should just see R something very close to 0. Maybe in our data we get something a little bit, just ever so slightly different from 0, like 0.01, because just something funny happened. Okay. So it should be R should be 0. Okay, but if, let's say, we get an unusual person with very big feet and a very high IQ. Okay, so this is an outlier out here. Outlier, giant feet, high IQ. Okay, and so the correlation is going to look at this point and say, oh, there is some kind of trend here. Okay, and then so with the outlier in it, you might see R is equal now to 0.4 or something like that. Okay, and you'd think, oh, maybe there's some kind of positive relationship here. Okay, and if it's even more extreme, so originally you would just get kind of something flat going through here. But now with this outlier, if we had to fit a trend line, it would look something like that, okay, trying to accommodate that thing. And so you might get some kind of correlation. So be careful in your analysis, okay? Correlation, R is unitless. Okay, and does not depend on the slope. Okay, so we could have two things, and here something like that. Okay, what is the correlation of this plot over here? This would be R equal to +1, right? What's the correlation over here? Huh? R is also equal to 1. So both of these have correlation equal to 1, even though the slopes are different. Okay. I guess unitless is maybe one word. Okay, so adding a constant, so positive or negative constant to the variable, or multiplying by a constant will not affect the correlation. So if we add a constant to all of the entire x column, and we recalculate the correlation between x and y, there will be no change. If we multiply the entire y column by a certain value, and we recompute the correlation between x and y, there will be no change. Okay? All right, I got another question for you guys. It's this one, question 3. So if the correlation between two variables is positive 0.95, then that means there is a strong positive linear relationship. Mm-hmm. 20 seconds to get your click in. Okay, I'm going to click call time there, and let's see. Oh, we're a little bit split here. The answer is B. Oh, okay. All right, because like I said, correlation only tells you the strength and direction. So it will be strong and positive. That much is true, but it does not tell you the shape. It will not tell you that if it's linear or not. So you cannot say that there's a linear relationship. So here's an example. So this data, if you analyze it, will have a correlation of about 0.95. I think it's 0.961 or something. I did the analysis here. But if we look at it, there's clearly some kind of curvature going on here, okay? So a linear relationship would not be appropriate for this data. And so correlation, again, on our previous slide, oops, where did it go? Yeah, R will not tell you the shape, okay? Our interpretations of R only work when the relationship is linear. R will not tell you the shape. So that's that, okay? All right, let's try this question. Let me get the clicker started here. Right. So this is question 4 here. Okay. The correlation between, sorry, I'll let the clock run longer. The correlation between people's height measured in inches and their weight in pounds is 0.72. If we measured their weight in kilograms, 2.2 pounds, then the correlation between height and weight would be all right, so I'll let you guys let's say another 10 seconds here to get the last few people's clicks. Okay, I think that's how many people we've got here. I'm gonna hit time. Let's see. All right, and indeed the answer is C. Okay, so converting from pounds to kilograms involves multiplying or dividing by 2.2. So that is just multiplying our data values by a constant. So like we just stated in our notes, that will not affect the correlation. Okay. Good. Okay, so adding a constant to the variable or multiplying by a constant will not affect the correlation. So in other words, another way of saying this, or another, I guess, a side effect of this is that generally unit changes have no effect on correlation, okay? Okay, because almost all unit changes involve multiplication by a constant or addition of a constant. So even Celsius to Fahrenheit, it's just addition and multiplication. So that will not affect your correlation. I guess and another thing is, and I'll squeeze this here, the correlation between x and y is the exact same as the correlation between y and x. So the order of the variables in which we calculate correlation does not matter. Okay, so when once we have correlation, it can be useful to then try to model a linear relationship. Okay. And so this is fitting a trend line, okay? All right. So this is, we are trying to model, we try to model the relationship between x and y, okay? And so our example that we will use, I'm going to just take this from the textbook, is that we are looking at, we've got some kind of book, all right? So this is my beautiful artwork here, okay? And what we're going to do is we're going to measure the width of the book, okay? And then we're also going to look in the book and count how many pages. Okay? And so our data set is going to consist of two variables, the pages and the width. So the width is in millimeters, and the pages is a count, so it's just the number of pages, all right? And, who knows? And so we've gathered some data. Let me just I'm going to just cheat here and copy the graph. The graph between the number of pages and the width. Okay, so if you want to redraw this, you can. Okay, and so we've gathered data across. We looked at a bunch of books, and we say something like, some book, maybe this one right here, has 620 pages, and has a total of and is 28 millimeters thick or something. Okay, and we look at another book, and it's got 210 pages or 230 pages, and it's 14 millimeters thick or something like that, okay? So on and so forth. We've gathered data on a bunch of books. Okay, and we've created a scatter plot, and it looks like there's a linear relationship, which makes sense, right? If a book has more pages, we expect the its width or its thickness to increase. And so in our textbook, they've already fit a trend line, okay? And so let's take a look at this trend line. So if you think back to the days of algebra, you know, you'd probably say the equation of a line is y equals to mx plus b, right? Y is equal to the slope times x plus an intercept, okay? In our case, we have the same thing, okay? In our case, the y variable is going to be width, and our x variable is the number of pages, okay? So instead of saying y is equal to mx plus b, what we have is we actually write it this way. We write y is equal to the intercept plus the slope times x. Okay, and that's what we've got here. So here it's our width, and it's important that we write it's our predicted width. Our predicted width is equal to our intercept, which is 6.22 plus 0.0366 times our pages. Okay, our x is the number of pages. And this is the equation of the red line here, okay? The equation of this red line. This is called the mean relationship line, okay? The mean line. Because you can imagine we might be able to, if we looked at a whole bunch of books, okay, we might have several different books that are all 400 pages long, okay? We might have 10 different books that are 400 pages long. All 10 of those books might not have the exact same width. However, if we looked at the width of one of those books, or if we looked at the width of all of those books that had 400 pages in it, we would expect the mean of those numbers for books with 400 pages to be very close to what this prediction line says, okay? So, so let me just write this out. So for a book with 400 pages, what will we predict its width to be? Okay, we predict the width is equal to, so our predicted width would be 6.22 plus 0.0366 times the number of pages, which in our example is 400 pages. Okay. So let me pull up my calculator. Okay. So I'm going to say 6.22 plus 0.0366 times 400. No, I don't want that. Is going to be 20.86. Okay. So this says 20.86 millimeters. So we're predicting a 400-page book to be about 21 millimeters thick. Okay. And that is what this red line says, okay? So 20.86 would be exactly on the line, okay? So this is a point on our prediction line. Okay. May I flip to the next slide here? All right. And so again, that value of 20.86 millimeters is our prediction for a book that is 400 pages. Okay. But of course, you know, any individual book, you know, we might find a book that is 400 pages long is not necessarily 20.86 millimeters thick. Okay, but if we, gathered a whole bunch of books that are 400 pages long, okay, not 400 books, we gather many books that are 400 pages long. Okay, we expect the mean of those books, the mean width of those books to be close to 20.86. Okay, so our trend line, also known as our regression line, okay, is sometimes called the mean line, okay, because it shows kind of the expected mean that we would have based on the data. Okay. This line of best fit, okay, the best fit line is determined, okay, or this regression line, the slope and intercept of the regression line are determined by trying to minimize the sum of squares residuals, okay? Now I will write this out and I will explain what I'm talking about. Okay, so go ahead and write that out. Okay? What is a residual? A residual is equal to the difference between the actual value of a data point and the predicted value for the data point. For the data. Okay, so in this previous slide, I'll let you guys finish writing that down. In the previous slide, it is essentially the vertical distance between a data point and, so I'll just get rid of this in a moment here. But basically, if we look at this data point here, okay, according to the trend line, we're predicting that the data point, 600 pages should have this thickness. The actual data value is up here. It's, I don't know, it's thicker than what we predicted. So this vertical distance, that is our residual, okay? And so what the best fit line does is it's trying to minimize the sum of squared residuals. So we're finding the squared size of the squared residuals. The residuals, we square them, and we're trying to minimize the total sum of those. There's a cool little thing online. Let me just find it. Visually. I'll explain visually. Okay, so here is some, let me zoom in here. Okay, and we want to know, hey, so here are just some data points that you know, we can move these data points and see how that affects the thing. But basically, it says, you know, with these data values, the best fit line is having an intercept of 5 and a slope of 0.81. Here we are relating someone's size of their hand to their height. So we're trying to predict someone's height based on the size of their hand. And how do we know that that's the best fit line? Okay, well, we can try changing the intercept and the slope, okay? And so watch what happens. So this red line up here is clearly not a good predictor for the data, right? It doesn't even run through the thing. And we can see the vertical distance from this purple dot to the red line is this much, okay? And if we square that, we get this, this box, okay? And so what this is showing is it's showing the total sum of squares of the residuals. It's squaring each of these residuals, okay? And it's showing this is the total area if we make the intercept 21, okay? So I can kind of move it around and we see, oh, okay, maybe somewhere around here is good. Our boxes are a lot smaller. The vertical distance between each data point and the red line, the line that we're trying to fit, is much smaller, okay? We can also change the angle here, okay? And so here we can start trying to shift things around, and we can see we're trying to minimize, we're trying to find the combination of slope and intercept. It's not the slope and intercept that minimizes the total sum of squares. Does that make sense? Can you guys see that here? So we're, you know, by moving the trend line around, we can change how much error there is between each individual dot and where the trend line says it should be. Okay, and so the one that fits the best is going to have an intercept of 5 and a slope of 0.81. Okay, and so anyway, this is just showing what we're doing. So we're trying to minimize the sum of squares residuals there. Okay. So if you do some calculus to try to solve this as a problem, you're going to find that the slope and the intercept will actually have these nice little formulas that we can use. Okay. And so the slope and intercept of the regression line, okay, which is also known as, you know, we called it the mean line, the trend line. This is also called the least squares line because it's the line with the smallest amount of squared residuals, okay? The slope and intercept of the regression line will have the following values. Okay, so the slope, the symbol we use for slope is B, and this is going to be R SY over SX, okay? And the intercept, you got to find your slope first. It's going to be Y bar minus B times X bar, okay? And so to calculate your slope and intercept, you need the following 5 values. Five values from your data. Okay. R is the correlation between X and Y. Okay. You need X bar, which is the mean of the X values. y bar, which is the mean of the y values. You need s sub x, which is the standard deviation of the x values, and s sub y, which is the standard deviation of the y values. Okay? So, you know, you've got a grid of numbers. We can look at, you know, whatever it is, hand size and height. Okay, and you've got, you know, 12 and 70 or whatever it is. I don't know. Okay, all of these numbers, you've got a bunch of numbers. Basically, you take your x values and you can find x bar and s sub x. You take your y values and you can find y bar and s sub y. And then you find your correlation between these two. Now, correlation, we have not gone over the formula for correlation. So I'm just going to say this is a complicated formula that you don't need to worry about. Okay? And nobody calculates correlation by hand. We could, if we really wanted to. We have the formula. We could do it. But almost always, we just take all of our data points, we throw them at the computer and say, hey, can you do this for me? And the computer says, sure, I'll give you the correlation. And that's how we do it, okay? So and usually, we often won't even calculate the slope and intercept ourselves. We just say, hey, computer, can you do the slope and intercept for me as well? And it'll say, sure, okay? Generally, okay, correlation is calculated with a computer. Correlation is found with a computer. Okay. Slope and intercept, usually done with a computer as well, but it's relatively easy that we could do it by hand if we wanted to. The important thing, though, is being able to interpret the slope and intercept into something meaningful. But I think we're going to have to wait to cover that next week. So we will end today's lecture here, and you guys have a good weekend.